Welcome to Fundamentals of Artificial Intelligence. We continue our discussion on knowledge representation and reasoning. So far, we have examined first order logic and looked at how first order logic could be used for representation of knowledge in simple application domains. We have looked at how logical reasoning could derive facts implicit in the knowledge base. Particularly, we have looked at inference, a process to derive new sentences from already existing sentences. In the last lecture, we had introduced resolution and looked at two processes. One, the process of converting first order predicate calculus statements to clausal normal form, and another, the process of unification. Resolution was introduced in quite informal terms. Today, we will introduce more formally a general principle of resolution and particularly look at how a given sentence can be proved in a knowledge base. Resolution, as we have already discussed, is an important rule of inference and can be applied to only certain class of well-formed formulas which are called clauses. Therefore, the first step in applying resolution is to get to what is called the clausal normal form, and we have looked at this in our last lecture, how to get to the clausal normal form from first order predicate calculus well-formed formula. A clause is a set of literals representing their disjunction, and a literal is an atomic sentence or the negation of an atomic sentence. In resolution, we are picking up a pair of parent clauses, and from there we produce a derived clause. Resolution for ground clauses is what we will look at first. Now, ground clauses are those where no term contains variables. That is, we have ground instance of the literals. So, if we have two ground clauses, P1 or P2 or P3, so on and so forth up to Pn. So, that is the disjunction of P's, and another ground clause which is a disjunction of the Q's with the first literal being the negation of P1. Then in above ground clauses, if all of Pi's and Qj's are distinct and I want to resolve these clauses, clause 1 and clause 2, the resolvent of these clauses is computed by taking the disjunction of the two clauses. However, I would eliminate the complementary pair, that is P1 and negation of P1. Resolution, as we could see earlier in our discussion, allows incorporation of several operations into one simple inference rule. Like earlier, I had showed you how modus tollens and modus ponens could be seen as resolution. Let us look at a couple of more examples on the same lines. Here are the parent clauses P, and P implies Q, which could be written as not P or Q, and therefore using modus ponens I could write this as Q. The same thing I could do by resolving these two parent clauses, and I could have a resolvent Q. Similarly, if I have two parent clauses P or Q and not P or Q, I could do a resolution of this to arrive at Q, which is nothing but the merge operation. Arriving at tautologies can also be looked as resolution of two clauses. If I have two clauses P or Q and not P or not Q as my parent clauses, I could arrive at Q or not Q, or I could arrive at P or not P, which are tautologies. Here I have two clauses now, P and not P. If I resolve them, I end up having the empty clause. Now this is written by an empty box. That's the representation that we will use here for an empty clause. And if you take a moment to reflect, having P and not P is about having a contradiction in the knowledge base. A contradiction, when we resolve, we end up having an empty clause. The other example here is about chaining, which is if I have P implies Q and I have Q implies R. So these implications are now written in clausal form as disjunctions of not P or Q and not Q or R. And if I take these two clauses as parent clause and resolve them, I have not P or R, which is P implies R, and this is the inference rule of chaining. So what we have seen here is that I can see different inference rules as simple resolution. So resolution is a very powerful rule of inference. Having looked at this, let us now try and give a general resolution principle. In formal terms, the general resolution principle could be defined as follows. Suppose I have two clauses phi and psi, and there is a literal phi in my first clause and a literal not psi in my second clause, such that these two literals phi and psi have a most general unifier gamma. What that means is that if I take that unifier and operate on phi and operate on psi, these two will be equivalent. So I have a clause phi and I have a clause psi. Phi is a literal in the first clause and not psi is a literal in the second clause, and they have a general unifier gamma. Then we can infer the clause obtained by applying the substitution gamma to the union of phi and psi minus the complementary literals. So basically it would mean that if I have a clause phi which has phi in it, and if I have a clause psi which have a literal not psi in it, such that if I operate with a unifier, I have this equivalence of the given literals, then the resolution is defined as the union of phi and psi minus the complementary literals. So, given such a definition of resolution, the resolution derivation of a clause phi from a set of clauses delta is a sequence of clauses in which phi is the last element of the sequence, and each element that I get in the sequence is either a member of delta or the result of applying the resolution principle to clauses earlier in the sequence. And if that happens, I can write that delta derives phi. So, that means there exists a derivation of phi from delta. So, what I am saying here is the following. I start with a set of clauses delta and apply a resolution to this set of clauses. As I apply resolution to this set of clauses, I generate new clauses, and this proceeds until I generate the clause phi itself. Then I would say that I have a resolution derivation of clause phi. Let us try to understand this with this following example. I have a predicate here, Ix, to mean that x is intelligent, Hx to show that x has common sense. Let us take a constant d to mean d blue. So, the first statement is saying if something is intelligent, it has common sense. So, I am writing Ix implies Hx. I could write that as in clausal form as not of Ix or Hx. And then the second statement is saying that d blue does not have common sense. And here I have a statement which is saying d blue is intelligent. So, this set of clauses delta, I can now derive a new clause using 1 and 2. So, if I replace x for d, this my h of d and the negative h of d will go away. They are the complementary literals. I will be left out with not of I of d, and then I can look at the third clause together with the fourth clause, which is I of d and not of I of d. So, that will lead me to the empty clause. This sequence of clauses that I am getting starting from a set of clauses delta, finally arriving at the empty clause here, is a resolution derivation. And I can write that delta derives the empty clause or delta proves the empty clause. Very close to this concept of resolution derivation is the concept of a resolution graph. So, if I have a set of clauses delta as shown on the left of your screen, for ease of simplification of writing them, I have just taken propositional clauses, but it equally remains true for clauses that would have variables in them. So, here I have P, not P or Q, not Q or R, and not R. That is the set of clauses delta. And on the right of your screen is the resolution graph that I could generate by resolving clauses in delta So, here are my clauses from delta. I could resolve between P and not P or Q to get a Q. I could resolve not P or Q and not Q or R to give me not P or R, so on and so forth. So, here is a resolution graph up to the third level, that is, I have expanded to 3 levels of deduction. Now, one of the problems with such inference graphs, if you could see, is that they are very difficult to follow, and we would love something to be in a linear form. So, if we want to encode such graphs in a linear form, we would rather love that we keep the sequence of the resolution, and that is done by something called a resolution trace. So, we will now try to define what is a resolution trace. The resolution trace is a sequence of annotated clauses which are separated into levels. In the first level, I have clauses in the initial database, and then each subsequent level contains clauses with at least one parent at the previous level. Now, the annotations here specify the clauses from which they are derived. It is important for us to realize that the resolution trace actually captures the information of a resolution graph, but in a linear form, so that readability is improved and I can see how the resolution is proceeding. So, here on the left of your screens is the resolution trace of the resolution graph that we have seen little while ago. At the first level, you could see that I have all the clauses from the initial set of clauses delta, and from them I could derive 3 clauses Q, not P or R, and not Q. These 3 clauses form the second level of the resolution trace. The resolution trace, as you can see, captures the information of the resolution graph in a linear form. And finally, I can have the third level of the resolution trace, which is the clauses that I derive at the third level of the resolution graph. Now, a little reflection on the resolution trace vis-a-vis the resolution graph is important. If you look at the resolution graph and the resolution tree, it should be obvious that when I am doing the first level of resolution, I am restricted to taking things from the parent clause and generating clauses at this level. Next, I am generating clauses at the second level here. So, the resolution trace actually is searching the inference graph in a breadth first fashion. Now, having introduced the concept of a derivation and a trace, I would introduce what is resolution refutation. So, the resolution refutation of a set delta of clauses is a resolution derivation, that is a sequence of phi 1s, phi 2 up to phi n of clauses, such that every phi I is either in delta or follows by resolution, that is, it is a resolvent of prior clauses in the sequence. And in addition, we require that the final clause in the resolution derivation, delta n, is an empty clause. So, a resolution refutation of a set delta of clauses, to put simply, is a resolution derivation that leads us to the empty clause. if there is a resolution refutation of delta, then we say that delta, the set of clauses that I started with, is refutable. So here is the resolution refutation of the set of clause delta, because as you can see, I have a resolution trace, and in that resolution trace you can see that finally I have the empty clause. So the sequence of delta 1, delta 2 to delta n finally comes back with delta n as the empty clause, and that's the resolution refutation of delta. One interesting thing to note about this is that the set of clauses, if you look here, the set of clauses which had lead to a empty clause, that means which had proved to be refutable, is actually unsatisfiable, because you could see in the very first level I could have things like q and not q. Now let us try and understand what do we mean by unsatisfiability, and when can I have unsatisfiability in a set of clauses. Resolution is used in demonstrating unsatisfiability. So if a set of clauses is unsatisfiable, it is always possible by resolution to derive a contradiction from clauses in the set. In clausal form, a contradiction takes the form of an empty clause, which is actually a disjunction of no literals. So whenever we arrive at an empty clause in resolution, we arrive at a contradiction. Now demonstrating unsatisfiability for a set of clauses can also be used to demonstrate that a formula is logically implied by the set of formula. This is very important for us to realize, because this leads us to the concept of how we arrive at a proof of a given statement from a knowledge base. So for a set of clauses delta, we can show that delta logically implies a formula phi by finding a proof of phi from delta. That is, if we could apply some resolution and we could establish that delta derives phi, then we could show that delta logically implies phi. Now by the refutation theorem, we establish that delta derives phi by showing that the union of delta and not phi is inconsistent. So it is important for us to reflect what we mean by this statement here. Here we are trying to say that we can establish delta proves phi. For that, we will not derive phi from delta. What we will rather do is we will take the union of not of phi and delta and prove it to be inconsistent. Let me give you the intuitive feeling of why this would be true. Very loosely, you can think of this as following. When I have delta and add it up to not of phi, if that becomes inconsistent or unsatisfiable, lurking in this set of clauses somewhere I already have phi. That's why adding not of phi brings in a contradiction. And that is why the refutation theorem, we can show that delta derives phi by showing the union of delta and not phi is inconsistent. So if we show that the set of formula delta union not phi is unsatisfiable, we have demonstrated that delta logically implies phi. So let's try to understand the same from the standpoint of models. Just to remind you, a model is the domain paired with an interpretation. So a model for a first order language is directly analogous to a truth assignment for propositional logic, because it provides all the information we need to demonstrate the truth value of each sentence in the language. So, if delta entails phi, that means all models of delta are also models of phi, then none of these can be models of not phi, and thus delta union not phi is unsatisfiable. On the contrary, conversely, if we have delta union not phi is unsatisfiable, that is delta is satisfiable, let us assume an interpretation I that satisfies delta. So, as I satisfies delta, I does not satisfy not phi. For if it did, then it would make delta union not phi satisfiable. Therefore, the interpretation I only satisfies phi. Since this holds for any arbitrary interpretation satisfying delta, it holds for all interpretations satisfying delta. That is, all models of delta are also models of phi, and we can say that delta logically implies phi. Now, to turn this into a proof technique, this is what we have to do. We take a set of clauses delta, and together with that we take the negation of the goal not of phi and try to show that it is consistent and lead to a contradiction. If there is no contradiction, then the clauses must be satisfiable. If there is a contradiction, then delta union not phi must be unsatisfiable, and the process of finding a contradiction is actually called finding a refutation. If empty clause is produced from the clause set delta union not phi, then we have already argued, we can say that delta proves phi. Now, these type of systems are called resolution refutation systems, precisely because the process of finding a contradiction is called finding a refutation. So, in a resolution refutation, we first negate the goal. Negated goal is added to the set of clauses. So, I have delta union not phi. If phi logically follows from delta, the set delta union not phi is unsatisfiable. And then we have seen that if I have an unsatisfiable set of clauses, applying resolution repeatedly would eventually produce the empty clause. So, I would have delta union not phi entailing the empty clause, and then we have already argued that if I arrive at an empty clause, then actually I know that phi logically follows from delta. So, here is the resolution refutation and algorithm, the basic steps for proving a conclusion phi given the premises. So, let us assume we have a set of premises and all of these are expressed in first order logic. So, as I was emphasizing, the first step here would be to convert all sentences to clausal normal form. Then we negate the conclusion phi and convert the result into clausal normal form. Add the negated conclusion to the premise clauses and then repeat the process of resolution. We repeat until contradiction or until no progress is made the following. We select two clauses, we call them the parent clause, and then we resolve them together, performing all required unifications. Now, if the resolvent is an empty clause, we have already found the contradiction and we can conclude that phi follows from the premises. If not, we add the resolvent that we have arrived in the step C here to the premises and repeat the step 4. Now, if we succeed in step 4, we have proved the conclusion. Let us look at now a couple of properties of resolution. The first one states its soundness. So, resolution is sound. What it means is that any clause that can be derived from a database using resolution is logically implied by the database. Here is the soundness theorem. So, if there is a resolution derivation of a clause phi from a set of clauses delta, then delta logically implies phi. So, the special case of this theorem is the check for unsatisfiability for us, and the deduction of the empty clause from a database would mean that the database must logically imply the empty clause and therefore is unsatisfiable. The second property of resolution is something that we need to be very clear about when we are doing resolution refutation proofs. Resolution is not complete. What I mean by it is that by itself it would not generate every clause that is logically implied by a given set of clauses. For example, tautology is logically implied by every set of clauses, but resolution will not produce this clause from the empty clause. Now, resolution provides no way of using sentences involving equality and inequality relations. For example, if in a database I have sentences P A and somewhere an equality statement A equal to B. Now, resolution cannot prove P of B, which is very obvious to the reader because I can see that I have PA and I know P is equal to B, and therefore I should be able to get PB. Resolution cannot derive that because as far as the database, the relation constant equal is arbitrary. Now, to give its standard interpretation, additional axioms are required. We will look at this as part of our lecture today. However, resolution is refutation complete. That is, if I have a database without sentences that involve equality and inequality, then given an unsatisfiable set of sentences, it is guaranteed to produce the empty clause. It is this property of resolution that we exploit to get our proofs. So consequently, we have a proof technique to determine logical implication by negating the clause to be proved, as we have seen, adding it to the database and proving its unsatisfiability. This is precisely possible because resolution is refutation complete. The proof of refutation completeness is a little complicated and involves introduction of several new concepts and lemmas. I feel it is outside the scope of this discussion on a fundamental introduction to knowledge representation and reasoning. We will not cover it here. Now, let us take some time to understand the link between resolution and equality. Refutation completeness of resolution, as we have stated before, does not hold when databases contain the relation constant of equality, which is intended to be interpreted as an equality relation. Now, there is no mechanism for substitution of non-variable terms that are known to be equal. One way of dealing with sentences involving equality is to axiommatize the equality relation. Now we know equality is reflexive, symmetric, and transitive. So we could introduce into our set of clauses axioms to state equality being reflexive, symmetric and transitive. Here are the three axioms. For all x, x equal to x is trying to state that the equality relation is reflexive. I could have symmetric for all x, for all y, x equal to y would imply y is equal to x, and the transitivity of equality saying for three variables x, y and z, if x is equal to y and y is equal to z, this would imply x is equal to z. Another way to have refutation completeness of databases containing the equality relation is to supply appropriate substitution axioms. So this could substitute terms for terms in each of functions and relations. Now this would work if we have substitution axioms for every function and relation within which we want substitutions to occur. Now this would be tedious to write these axioms. There are other rules of inference called paramodulation, which when added to resolution principle guarantee refutation completeness even when involving equality. There are weaker versions of paramodulation called demodulation, and demodulation is the basis for the semantics of functional programming languages like Lisp. However, for our discussion here, we would not cover these rules of inferences. Let us now take a couple of examples to understand resolution refutation proofs. So here is our first example. Here is the premise. The first statement is saying if a course is easy, some students are happy. The second one is stating if a course has a final exam, no students are happy. The idea is to prove now that if a course has a final exam, the course is not easy. Let us take the following predicates. Now recall that a predicate is an assertion that some property or relationship for one or more arguments hold. So we take a predicate called easy x to say course x is easy. We have another predicate happy x to mean student x is happy. We introduce a third predicate final x to mean course x has a final exam. Now let's try and convert the premises to causal normal forms. If a course is easy, some students are happy. We can write this in first order saying for all x, x is easy. So course is easy. There exists some student who are happy. So here is the first order predicate calculus formula for the above statement. Now in order to apply resolution, this has to be converted into a clause. So the first thing that is to be done is to replace the implication. So the implication P implies Q is replaced as not P or Q, and now we will try to remove the existential quantifier. This is very important to remember from our last discussion that here this y is dependent on the universal quantifier x, and therefore we would introduce what is called a Skolem function f of x to replace the existential quantifier there exists y. Now we are in a position to move it to a prenex form, and we have our first clause which says not easy x1 or happy f of x2. Now this is important for us to realize that while coming from this to this clausal form here, we have replaced every variable with a new variable that's not occurring anywhere else. Let us now take our second statement. If a course has a final exam, no students are happy. So this again involves an implication, but then when I am saying no students are happy, I am looking for a negation. So here is the first order predicate calculus statement, which is saying for all x which have a final exam, there does not exist any y such that happy y is true. So no students are happy. Now when you convert this to a clausal form, this negation needs to be first pushed in to apply to only this portion or the atomic portion, and we push that inside. So not there exists y becomes for all y not of happy y. Thereafter we could eliminate the implication to write a statement saying not of final x or not of happy y, and all of the universal quantifiers are at the front. So from this I generate my second clause, which is not final x3 or not happy y1. Now remember, I have now introduced new const variables while writing clause 2. What I wanted to prove is the statement that if a course has a final exam, the course is not easy. That's my phi. So we have to first convert it into clausal normal form, and thereafter the negation has to be added to delta. So here is the statement: for all x, final x, if the course has a final exam, then the course is not easy. So that's what this statement is saying. So as before, you push the negation inside and replace it by for all y there exist has to be replaced now for all y, and the negation will go inside, and then you will have the implication replaced. So once I replace the implication, I have the following statement, which is saying not of final x4 or not of easy y2. So that's the clausal normal form of phi. Now in order to take this proof forward, I must negate the goal. So here is the negation of that statement, and this is like not of p or q, which should be like p and q. So I end up having final x4 and easy y2. Now this being a conjunction here, I can write this as two separate statements. Final x4, that's my third clause, and easy y2, that's my fourth clause. So the negation of the goal led to C3 and C4. I now have the resolution trace of these example. Here is the set of initial clauses that I start with, and I derive not happy y1 by taking clause 2 and clause 3. So taking 2 and 3, this final and not final goes away. So I have not happy y1. From 1 and 4, I could remove this complementary clauses easy and not easy to have happy f x2, and then I have a contradiction here from 5 and 6. Now how could I get a contradiction from 5 and 6? Intuitively, the clause 5 is saying that no student is happy. The clause 6 is saying that a particular student f of x2 is happy, and therefore I have a contradiction. Now, for the same resolution trace, I could create the refutation tree, and here is my refutation tree. So if you now see, I had my first derived clause f1, which is between C2 and C3, I had f1, and the substitution that was used while getting not happy y1 from 2 and 3 was that x3 need to be like here. I had the substitution for 2 and 3 as x3 for x4, and then I could have happy fx y2 from 3 and 4. So here is the refutation tree for the resolution and trace on your right, and we could see that we have arrived at a empty clause, a contradiction, after the goal was negated and added to the clause set. Hence the statement is proved. Let us take another example. We have an example here which says the father of someone or the mother of someone is an ancestor of that person. An ancestor of someone's ancestor is also the ancestor of that person. The third statement is saying Jesse is the father of David. The fourth statement is saying David is the ancestor of Mary. And the fifth statement is saying Mary is the mother of Jesus. Now we have to prove that Jesse is an ancestor of Jesus. First we look at the predicates. We have father x comma y, x is the father of y. Mother x comma y, x is the mother of y. Ancestor, x is the ancestor of y. And then we have to use a couple of constants. Now recall that a constant is a symbolic name for a real world person, object or even. So we have constants here, Jesse, David, Mary and Jesus. And let's look at getting to the clausal normal form for these statements. The first statement, the father of someone or the mother of someone is an ancestor of that person. Here is the statement which says for all xy, x is the father of y or x is the mother of y would imply that x is an ancestor of y. So in order to convert this to clausal normal form, you have to eliminate the implication. So we replace the implication by P implies Q as not P or Q, and then you take this negation inside and distribute over the or. So you end up having an and, not of father and not of mother, and this is retained this side. Now you have an and an or, and all we have is father or ancestor and mother or ancestor. So that leads us to two clauses for this first statement, because here is an implication and I can break it up into the two following clauses. Number one, not father x1 y1 or ancestor x1 y1, and the second, not mother x2 y2 or ancestor x2 y2. The second statement is here, an ancestor of someone's ancestor is also an ancestor of that person. So we could write for all r, for all s, for all t, r of s, ancestor r comma s, and s is an ancestor of t. So we could write r is an ancestor of s and s is an ancestor of t implies r is an ancestor of t. Now you replace the implication first, then you have negation and an and, you rewrite it using De Morgan's to not of P or not of Q, and this portion is already not of ancestor R comma T. So we have one clause coming out of our second statement, and this is the clause. Now the third statement is pretty simple. It's saying Jesse is the father of David. So we have a ground statement, father Jesse comma David, no variables in there. So it's already in clausal normal form. We have David is an ancestor of Mary. So we have ancestor David comma Mary already in clausal normal form. Mary is the mother of Jesus. So mother Mary comma Jesus. And now the statement to be proved, Jesse is an ancestor of Jesus. So here is the statement, ancestor Jesse comma Jesus, and you negate this to get our seventh clause, not ancestor Jesse comma Jesus. So this is our initial set of clauses delta, and we now look for the empty clause. So I take clause 3 and clause 7 and resolve them. But now kindly note a new introduction of the substitution that's being used, written in front of the annotation. So I have Jesse for R and Jesus for T in clause 3 and clause 7. So that leads to having Jesse comma S here from this first literal, and S comma Jesus from here, and this are the complementary literal pairs that will go away. The next is about taking 1 and 8. So in 1 and 8, you could see that we are talking of a substitution which is Jesse for x1 and S for y1. So that substitution will give us the number 9 clause. We then have 4 and 9 resolved, and here once we resolve 4 and 9, this father and father Jesse comma David, these are the complementary pair, and all I will be left out with is not of ancestor David comma Jesus. Next I have 3 and 10 to generate my 11th clause in the resolution trace. I go on forward like that, and I finally arrived at the empty clause. So arriving at the empty clause means that the statement that I wanted to prove is actually derived from the initial data base or initial set of clauses delta. Now to finally wind up this lecture today, let us quickly look at an example from the blocks world problem that we have been discussing. So here is a slightly different version of the blocks world example. Suppose there are 3 colored blocks now, and they are stacked as shown, where the top one is green and the bottom is not green. Now the question is there a green block on top of a not green block? Now intuitively you can very well see that the answer to this question is yes, because if B is green, then I have this statement being true because green is on top of non-green. Now on the other hand, if B is non-green, then also the statement is true because I have A, which is a green block, on top of the non-green block. How do you look at this in first order predicate calculus? In order to do this, I introduce 2 predicates on x comma y which holds if and only if block X is immediately above block Y, and green X, which is saying that block X is green. And is there a green block on top of a non-green block reduces to a query, there exists an X, there exists an Y on X comma Y and green X and not green Y. So these clauses are already in clausal normal form except the query. So I convert the query to a clausal normal form. This would require that I first convert this as for all X, for all Y not of the statement and take it inside. So I generate the clause for the negation of the query and add it up to my set of clauses. So all I am told here is that A is on B, and second B is on C, and I am told that A is green, and I am told that C is not green. So these are clauses C1, C2, C3 and C4, and I have the fifth clause, which is negation of the query. Now from 1 and 5 I could derive that X can be replaced by an A and Y could be replaced by a B to give me not green A or green B. And from 2 and 5 I could derive a statement not green B or green C. For when I am doing 2 and 5, I would replace X by B and Y by C. So I could have this statement. Then I resolve these statement 7 and 6 with 3 and 4 to give me two statements. So I can take 6 and resolve with 3, that will give me green B, and I can take 4 and resolve with 7, that will give me not green B, and that could lead to a contradiction. Now when I have a contradiction in this problem, the knowledge base entails that there is some block which must be green and on top of a non-green block. However, it does not make any commitment to any specific one. Specifically, the whole resolution that I have performed does entail this existential statement, but in no way entails what is X or what is Y. So a general method for dealing with such scenarios has been proposed, and this method is called the process of answer extraction. We will look at answer extraction in our next lecture. Thank you.